Well, thank you, everybody. So just a little bit about me. As you heard, I'm CTO at Paremus. I've been working with OSGi for a long time. I'm actually a co-chair of the IoT expert group, but I also do a lot of work with enterprise OSGi and have done for quite a while. I have a book on the subject. But what I'm here to talk to you today is a bit about push streams, and that means we're going to have to think a little bit about how you work with data. So data is everywhere, and you've got Java's collections, which is how a lot of us think about interacting with data. So we've all written code that looks like that, right? And probably code that looks like that. And hopefully many of us have progressed onto writing code that looks like that, because we were allowed to start using Java 5 a long time ago. And, you know, it's easy, right? But you can make some mistakes, and it's not always obvious that you've made the mistake. So, for example, this is a really bad way to iterate over a linked list, and it's one of the reasons we're told not to do it. And it's part of the problem is we've got this external iteration. We've pushed control logic into the code, and if we wanted to parallelize this, say, it would be a massive task, because all of the control logic is for us to provide. And we've got to do that combined with our business logic. And Java 8, they basically fixed this. They said the collections API needs to be modernized. We need internal iteration. And they added a load of functional concepts into the Streams API, which made this even more powerful. And it's pretty simple, the concept of streaming a collection. So you basically take the collection, ask for a stream of it, and then you can do things like for each, so perform an action on every item. And because we've separated what we want to do from how we're going to do it, life is a lot better. Parallel processing can be implicit. If you've got a parallel-capable collection and you want it to run in parallel, well, great, it already can. And you've got functional pipelines which allow you to build up really simple processing. So in this case, if you wanted to find a list of children who were signed up to a service so that you could send out some protection notice, you might want to know how many there were first. So these are things that we call intermediate operations. So those are things that happen in the middle of the stream. And then we also have a terminal operation. And that's the thing that's going to actually give us an answer at the end. And these are important to know about. So Java 8 streams have a number of useful properties. For example, they are lazy, which means that we only process the data in a stream on demand. We don't actually eagerly process anything. And it's calling the terminal operation that actually triggers this processing. So if you start creating a stream and you do a load of intermediate operations and never call a terminal operation, you will process none of the data. Streams can also short circuit. So there are operations that don't require you to see the whole stream to get the answer. For example, find first and find any are really good examples. Find first, once you've found the first thing, who cares about what the rest of the stream does? Similarly, find any will give you just any one that it finds. It doesn't need to keep looking afterwards. But importantly, all the way through, we're pulling data from the stream when we call that terminal operation. That's the point at which we start grabbing, sucking data in as fast as we can until we reach the point at which we can stop. So just to go back and say, before Java 8 came along, when we talked about streams, what people meant was they meant an input stream, right? So it was really kind of them to reuse that and not at all confusing. And whilst you didn't think about it, you actually still do iterate with a stream. So this is quite an inefficient way to read from a stream, but it is what you're doing. You're reading from a stream by iterating over the bytes. But the big difference is an input stream may block, so we don't actually know how long that's going to take, whereas we can make a decent estimate for a list of a given size. Your thread can actually get stuck if you're waiting for user input from a keyboard, or you're waiting for something to come in from the network. It could be a long time that you sit there trying to read in that loop. Obviously, we've got Neo, which can be non-blocking, but it is a lot harder to use. I mean, how many people here write raw Neo code whenever they need to do I/O? Yeah, that's about what I figured. So basically, an input stream is an ordered collection of bytes. That's kind of what it is. So it could make sense to try and stream over those bytes. We need to maybe do some mapping. We need to process them. So is there a reason why we don't do a for each on an input stream? Well, there is, and it's that it can block the thread indefinitely, potentially, which it could be a real problem. If you've got an asynchronous input, so a user typing at a keyboard, or data coming in over the network, then you're wasting a huge number of resources by just waiting in this loop. You've blocked the thread, you've blocked whatever other processing could have been happening. But the other problem is that if you've got a slow processing function, then data may arrive faster than you can cope with it. So we heard Ray talking about bursting out to try and take things that are using up most of the CPU on your box. If you've got data that's coming in and you can't stop the hose that's coming at you, then you better be able to process it fast enough. And if you overload the consumer, that's effectively what we call a denial of service attack. And this is independent of whatever the data type we're talking about is. So I've talked about collections, which hold objects, and I've talked about streams or input streams, which hold bytes, but the concepts are the same. It doesn't really matter what you're processing. You need to be able to cope with these things. And Java 8 streams just can't. They're not asynchronous, but they weren't designed to be. It's not that they're bad, it's just, you need to use the right tool for the job. So what we really want is we want some kind of stream, like a Java 8 stream, but that's push-based. And that may seem a bit complicated, because actually a push-based stream is just a fundamentally different thing from a pull-based stream. You've got your function that's being called as data arrives, not when you finished the previous call. So if you've got 10 threads pumping you with data, then yeah, you'll get concurrent calls. That's just the way life is. On the other hand, it means that we've got the opportunity for really high throughput and really good parallelization, because you've got data coming in, potentially on lots of different threads, and you can just process it as soon as it's available. So the terminal operations, though, in order for this to work, need to be asynchronous and non-blocking. If your terminal operations aren't, then your stream isn't really operating on a push principle. You've got threads that are stuck waiting for stuff to happen. So what we've got here is we're looking for something that's a primitive. So promises are the primitive of asynchronous programming. That's how you deal with a value that doesn't exist yet. So rather than returning values from our terminal methods, why not return promises from our terminal methods on the stream? And because we've got this result that will be resolved later when we get the eventual value, we've actually made ourselves non-blocking. OSGi has promises. Those could be worth a try. And so we look at the Java 8 stream. So it has this rich and powerful API, but it turns out making it push-based is easier than you might think. Because if you just change the return type of those terminal operations, suddenly this thing has become asynchronous and has become able to cope with incoming asynchronous data. We're no longer saying we will process until we find the total count. We're saying we will have a result which shall resolve when the count is available. There are a couple of problems. And the main one is, how do we know when the stream is done? Because it's a lot easier with an iterator than it is with just a stream. Because the iterator gives you a nice handy method to say, there's no more data now. So you know that you're done. Pull-based iteration also has this wonderful property of being essentially self-managing in terms of the resources it consumes. Because you process the elements in turn, you've got this break on how fast you're going to try and consume things from the stream, from the thing that you're iterating over. Whereas your push-based system can receive an event storm where suddenly you lock up all your threads trying to process the big batch of data that came in all in one go. And that's not good. And in fact, even a single producing thread can be enough to totally overwhelm a system if you're not careful. If you set up a denial of service attack right, you don't need very many client machines to completely overwhelm a relatively sophisticated system. It's surprising, but it can really cause a lot of damage. So how do we fix this? Well, just pushing the raw data in was the simple option, but it's not enough. We need to get an event that tells us that the stream is done, that there's not going to be any more data. You also need another one to say, actually, the stream is finishing now, but because something went wrong, that there was a failure. I can't give you any more data, but we didn't reach the end. So we've got this simple wrapper that we can create, which is basically, we've got an event, and the event is going to be one of some data, of which hopefully you'll get a lot, an error, which hopefully you won't get at all, and a close, which you will get when the data eventually reaches some endpoint. So we've got that event, and we're starting to kind of come together, but we should also pay attention to problems that we've solved before in computer science. And actually, if you look at a push stream, there's a lot of similarity with the way that network engineers are used to working. So you've got asynchronous delivery, you've got a producer and consumer that may run at very different rates, and you look at TCP. So TCP has the concept of event storms. Someone can just be sending packets far too fast. And the way you cope with that is with back pressure. So the person consuming the data from the TCP connection gives back pressure by ACK or NACK. And because of that, it can allow the producer to not produce data at a rate that totally overwhelms the consumer. So the way it works, for those of you who are really interested, is the producer will start at some rate and keep getting faster until the consumer doesn't ACK fast enough, at which point it'll throttle back a bit. And that's how you maintain really good use of the line speed when you don't actually know what the line speed is and whether you're faster than them or whether they're faster than you. So our push streams need this sort of feedback mechanism. We need a back channel to say, OK, you're going too fast, or I'm good, keep going. And the simplest way to do that is to actually just have a delay that says, don't call me for a bit, I'm busy. And this is where we come up with this functional interface. So for consuming asynchronous events, we've got push event consumer, which accepts a push event and returns a long. You can detect an end of stream because you get the event, and you can return this back pressure. If the back pressure is positive, then wait at least that long. If 0, then just keep sending me data, I'm doing fine. And if negative, close the stream, I don't need any more data. And this is really important because this is what allows us to do short-circuiting, because it's possible we don't need to see the whole stream. It's possible that we'll reach a certain point and say, I have enough information to do what I need to do, at which point you want to tell the person that they don't need to keep sending data at you. So it's really, really important that we have that ability to feed back. So buffering. This is something else that people will be used to if they have done much work with networking. So an event consumer may receive events on lots and lots of threads. You have no real control over how stuff is pushed to you. You may also be very slow. So what buffering lets you do is it allows you to switch the thread. So rather than using the incoming thread to do a big, long, slow operation, you can return their thread back to them and put the work into a buffer and then use your own thread to process it. It also means that you can scale up or down the number of workers. So say you have 10 threads feeding data to you, but you only want one thread to actually do the processing, you can do that with a buffer. Or the opposite way around, if you have one thread pushing data at you very fast and you need to scale up, you can have 10 threads that are actually doing the work. And all that happens is incoming data is queued until it can be processed in your buffer, and then you consume stuff and it shunts down the buffer. It's not really very surprising. And the buffer itself can then return back pressure based on how full it is. So you've got data being pushed into the buffer, and the more full the buffer is, the more you can tell the producer to back off. And this is a built-in feature of push streams. So we've got then the question, what happens when our buffer gets full? If our buffer's full of data, what do we do? Well, the cheeky answer is to say make the buffer infinite, but memory isn't infinite, so that's not really an answer. We could try and slow them down by blocking their thread, but that's not really an asynchronous way of dealing with this problem. And one very good option, actually, is just to close the stream, because we've reached a bad situation. We've reached the point where the buffer we created to hold these events was insufficient, so something has probably gone wrong. This is called a circuit breaker, and it's exactly the same sort of thing you'd get if you had an electrical problem in your house, and there's too much current, or you end up in a situation that you shouldn't be in, and all you do is you just trip, and you say, stop, because at least that way I'm failing safe. I'm not going to cause a cascading failure throughout the rest of the system. And it's how you protect against event storms. You just basically say, I am not accepting more data from this place, because it's overwhelming me. So windowing is another interesting option. So you may wish to process events in batches. So you can then aggregate those things together, turn them into a single event. And that could be based on an absolute number of things, or it could be based on a time window. Because sometimes what you want to do is you want to have a sliding time window, or you want to be able to aggregate over a particular length of time so you can work out, say, a rate, for example. And the underlying behavior is really similar to buffering. You've just got an absolute number that you hit the mark and then ship off to the person, or time where you gather up for a particular time and then you say, I've hit my time window, whatever was there is what you get. So we've talked about consuming events, which is great, but we actually kind of also need to know about how we make them, because it's not very useful being able to consume something no one can produce. So event producers are connected to consumers using the open method. So here you connect these two things together and you get given a closable. And you can use that closable to end the stream. So there are three ways really that we can think of a stream being finished. You've got the person producing the data says, this is the end of the data. You've got the person consuming the data saying, I don't need any more data. And then you've got the third party, the person who put these two things together, saying, I'm closing this now because we've reached the stage where I think enough has happened. Closable is also very useful because sometimes data streams are infinite. You may not think infinite streams are that useful, but they turn out to be really, really common. So things like the stream of click events from users, if you're doing metrics for web server monitoring, there's no end to that. There's no end to the temperature readings from a temperature sensor. Hopefully there's no end to your fire alarm reporting the status of your house, because if there is, it probably means there's been a really big fire. So, helpful behaviors. We're talking about producing events, and we want to make this easy. Now, you saw the interface we had defined. That means you've got to be able to cope with multiple simultaneous registrations, and that's hard. You also have to be able to handle back pressure from the consumer, and that's hard too. So in some sophisticated scenarios, it may be useful for you to do that yourself, but actually, we want it to be easy to produce events. And sometimes you've just got no choice about waiting. I talked about receiving metric events from your web server as people make incoming requests. You can't tell all your users to click more slowly. That doesn't work. You just have to deal with the data arriving as it does. So we don't want it to be hard, so we'll provide some help. And this is where the simple push event source comes in. So this is something that we provide to make it easy to use. You've got a buffer built into it with a circuit breaker, so you don't need to worry about back pressure. You just push data in at the rate that you push data in, and if the simple push event source is set up with the correct buffering characteristic, i.e. the right size buffer and the right number of consuming threads, then it will never get full. And if it does get full, then it will go pop, and you'll get a nice big error message, and it will tell you about what's going wrong, and possibly that you're receiving some kind of denial of service. You also have this really useful thing called a connect promise. And the thing that the connect promise does is it allows you to actually know when there's someone listening. Because one of the things about asynchronous event delivery is You can keep providing data to someone, but you don't necessarily know whether they're interested or not. And it's really useful to be able to optimize this case by not starting event delivery until you know someone really cares. So I've been talking at you for quite a while now, so I figured it was probably time I showed you something a bit more fun. So time to play with some push streams. So we need an asynchronous source of data, and it turns out that the UK rail network is very much behind open data, and they've got an API which does streaming data. So there are batched events, which are just a big lump of JSON, and then you can process that JSON, and it will tell you information about what's happening on trains in the UK right now. So, resolution has changed and completely killed my editor text size. So let's get that to the point where you can see it. Is that text there big enough? Can people see it at the back? I'm seeing nodding. I'm going to go with it. So what you can see here is some code which is actually doing the Stomp message processing. Now, I don't know what you know about Stomp, but it's basically a streaming text protocol. It's a bit like HTTP, but designed for streaming stuff at you. And it turns out there are no good Java clients, so I had to roll my own using Netty. So I've got a really simple state machine here where we're receiving the various messages. So you get one connected, which is when TCP connection comes up and the server says hello. And you can see at that point I'm doing some authentication. But when I talked about that connect promise, and you can see what I've got here is saying I'm going to hang off this connect promise, and when that connect promise resolves, so when someone connects to my stream, I'm going to actually subscribe. So I've created a connection to the server, but what I haven't actually done is started asking for any messages. So I'm not consuming resources on their side particularly, and I'm not having to deal with data that I don't need right now. But when someone does connect, I'll do a subscription, at which point I'll go through my subscribe loop and I'll start receiving messages. And then in here you can see I'm just publishing the content as a string, because that's what Stomp gives you. And then if I'm no longer connected, at that point I'll unsubscribe because I no longer need any data. So that's all kind of cool. That's using the connect promise. But the thing that's much more fun is actually looking at what we are doing. So for those of you who've used Java 8 streams, hopefully this will be quite familiar. But we're actually getting hold of a push stream from the push event source that we were using earlier. We're doing a flat map operation. So flat mapping is turning one event into lots of events and then processing them in turn. So that's saying we know we had batched messages. So we're basically breaking up the JSON batch into lots of individual messages. We're then looking for a message that has a header and has a message type of 0003, because they gave a really nice, easy-to-understand human-readable API where there are integer codes with prefix zeros. But this is basically just saying we want something that's a train movement message. So this is telling us that a train has gone past a particular sensor point on the UK network. We're then going through converting that using Jackson, and then this magic bit here. So it also turns out that they have this really useful thing where you take something called a stanox, which is a unique identifier for a location on the rail network, and bears no relation at all to GPS coordinates. So if you want to actually know anything useful about where it is, you need to find a lookup table, and that's all we're doing here. And my lookup table is incomplete because it turns out that it's not all publicly available. Apparently there's some kind of terrorism alert if you go and search for too much of this stuff. So what we've got is we're looking for ones where we know actually where the reporting location is. We then do a mapping into our useful object here, where we basically say where is the current location, where's the next location going to be, who's running the train, some information about it. And then this last thing I'm doing here is something I had to do because it turns out that whilst we joke about how terrible British trains are, there are a lot of them. And whilst this bit can completely cope with the data rate, like easily, my JavaScript UI isn't so good at coping with huge numbers of train movement messages coming in simultaneously. So I filtered it to only be trains that are running late, which actually is a lot fewer trains than the total number of trains, which is a good sign for our rail network. So on the actual UI side, what we have is we have an asynchronous servlet. So this thing is basically just allowing you to subscribe to an event stream. And you see it's using actual async servlets. So the one consuming thread from the Stomp message is pushing all the way through and can cope with, I've tested it up to about 80 simultaneously connected clients. And this is just on one thread to show you how efficient you can be with a push-based kind of algorithm. And here you can see we've got a build pipeline. And if I show you that, we just do a little bit more stream processing on this. So we get hold of the stream of train data. We do a reduction across all of the different ones that we can be connected to. So if we have multiple sources, we can merge them into a single stream. And we then basically write it out as a set of text events. And the end result is something that looks help if I actually started it, wouldn't it? The end result is that's just DS complaining because I don't have metatype installed. There we go. So this, as you can see, is a map of the southeastern UK. And these blobs coming in, these are live reportings of trains that are currently running late. Now, we're after rush hour, so there aren't as many as there were previously. But you can see in London, we've got quite a few. And if I zoom out, you'll see it's mostly around centres of population, which is what you'd expect. So London has quite a lot. You have Manchester and Liverpool up in the north here, and then off into Newcastle. And interestingly, whilst I was told this was UK-wide, I've yet to see any events come from Scotland. So I'm wondering if they've already decided to declare independence from the UK rail network. And you can see here, this is real live data. These are genuine trains that are currently moving around the UK rail network in various parts, all being processed with push-based data. Pretty simple, really. So I hope you find that interesting. I certainly had a lot of fun, because everybody loves trains, right? What I will do is I will go back, and I do have one more thing to show you. So also I should just quickly say that you've got more information about push streams in the OSGi design repository, so you can see this, it's coming up in the next OSGi specification release, release 7. There's a draft specification which includes push streams. Apache Aries has the implementation that I'm using right now, so that's available in Apache snapshots. You can start playing around with it.